Okay, so let's start now. I think see, we are actually having exam tomorrow. So what we'll have to do is we'll get to know like uh, what all are important topics for the tomorrow's exam, right? So let us understand the these algorithms first. What are these algorithms? So I think basically from week 7 we have three algorithms. Which are these three algorithms? One is k nearest neighbor. The second one is decision tree, and then we have a generative model, right? So, or whether it is a generative or a discriminative model, naive based
Generative.
generative, right? And we'll understand what is the difference between all of this, and then uh, decide based on that. So I have a few slides over here. Maybe I'll just try to show you these slides. These are not the same slide as that of a professor has taught. Little bit different, but let's try to see those also. And so, okay, okay, right. Three, two. Okay.
Sir, are you sharing your screen?
No, no, no. I'm yet to share. I'm just downloading all this PDF to show. One more thing. What about K nearest neighbor? Do actually this algorithm learn anything from the data?
No.
No.
No, right? Uh, so basically, your k nearest neighbor is that kind of algorithm where you just based on the Euclidean distances, you try to predict. So every time whenever you have any test data point, what you will have to do is you will have to uh, calculate all the distances and check whichever is nearest to Earth, right? So but and what is the difference between a parameter of uh, and an hyperparameter of, let's say, any algorithm, or maybe I can say any population, or related to or how you wanted to differentiate between a parameter. So we have seen some parameter estimation techniques, we have seen some hyperparameters. So what is the basic difference between a parameter and hyperparameter?
Hyperparameter has to be found by the validation method.
Yeah, so generally hyperparameter uh, we don't learn, right? We'll have to like cross validate, or you can say that maybe you wanted to find it out using the trial and error methods, right? And if you see the parameters which you have estimated, we have certain techniques to estimate those parameters, and which all techniques we have seen in this course. I think,
MLE.
yeah, MLE we have seen, so which is the maximum likelihood estimator. So generally, you'll have given some samples. What do you think about the sample, or uh, we are actually assuming that the samples are coming from a certain population, and that population will have some probability distribution. So whenever you have any probability distributions, the parameters are associated with that, right? So for example, if you have a Bernoulli distribution, the parameter there will be your probability of success, that is P. If you have normal distribution or Gaussian distribution, you have two parameters associated with that, which is, one is what the mean, and another is a variance. So using this techniques, we try to, since we do not have actual understanding of what these parameters are, we try to get a sense of these parameters by using the samples which are there with us, right? So to estimate these parameters, we use different techniques. The important techniques, probabilistically, we if you understand, is the maximum likelihood estimator technique, right? So yeah, and whatever we are speaking right now, these three algorithms, which is k nearest neighbor, another one is uh, decision tree, and the third one is the naive bayes. Let's say, what about these techniques? They are the supervised learning techniques, but they are the classification techniques, right? You try to classify the uh, you know, so your labels, right? Out the labels will be discrete values. They are not the continuous values as we see in the regression. Is that correct? Sorry. Right. Okay. So I think I'll not go into the theory much, since we have seen already this theory. I'll just try to find. We'll see only the algorithms, which is the basic algorithms, and then based on that, we'll try to understand some of the maybe you can say the numericals, or like how to find out the answers to the questions, right? So that is more important. I think that is for the today's lecture. So this is the k nearest neighbor. What does this k represent here in the k nearest neighbor? This k is what? Uh,
Hyperparameter.
it's a hyperparameter, right? So what will be the value of, so if you have a data set which contains n examples, right? For example, or n samples if you have. So how many minimum and what will be the maximum value of this k neighbors, or what is the minimum and maximum value of this k?
Minimum is 1 and maximum is n.
In, right? So that is the point in here, that we can have minimum one neighbor, which is the nearest one to the data point. So what we do in this algorithm is, you have a data set, right? Maybe that training, during your training. Okay, again, this is, since it is a supervised learning algorithm, that means what things are available to you. You have the input features and you have a labels, right?
Label.
So if you have input features and if you have labels, then what do you do then? So and what is the nature of the input features? Uh, let's say each of this feature is in d dimension, or each of this example will contain d features, right? So the data set will look like, so okay, so you have some d features. D features means like how each of the example will look like. So suppose x1 is one of the example. It will let's say if I wanted to see it as a vector, how this will look like. It will have
D
8 features, right?
one D cross 1.
Yeah. Right. So d cross 1. And now what you are trying to do here, so that means you are seeing this data in a d-dimensional space. Is that correct? If you have d features, then that means each of this data point will lie in a d-dimensional space. So let's say how you decide that whichever is the class. So corresponding to each of this data point, we have the corresponding label, right? Correct. So in that, during training, I know that which all are. So maybe I'll just try to show you how does this look like. So if you have let's say x1 as the data point, and it has some values f1, f2, right? And you have some x2, which again it will have some values related to. So maybe I'm just writing this f1, f2. What does it mean? These are some values for the features, right? Uh, okay, maybe I'll just write something like 1, 2, and let's say uh, 3, 5, right? And its corresponding label is, let's say, plus minus 1, and here the label is plus 1. You have another data point which is, let's say, 0, 0, and its label is minus 1. One more data point x4, which is what? What is the let's say, okay, any data point with uh, 2, maybe 4, 6, and its corresponding label is. So this is the generally your data set looks like. So in what dimensions this data set is there currently?
Two.
Yeah, so if you don't consider these labels as a third dimension, you can understand that this data set is in the two dimensions, right? So if I try to plot this, since we can plot this two-dimensional data set easily, so if I try to plot this data set, how does this look like? Let us see. So, right, so first data point will be where uh, 1 2. So that means if I just roughly see this is my data point. The second data point will be 3 5, and okay, third I will just plot it. The third will be here, this 1 2. I'll just say that this is x1, this is x3, and then you have a data which is 3 5. So 1 2 3, uh, 3 4 5, somewhere here, right? And 4 6 will be suppose somewhere here, right? So we know the labels corresponding to it. So this, let's say this is a positive class, this is a negative class, right? So this is the negative class. So what does this algorithm do is, this already uh, before. So this is your training set, right? So that this information you already know. Now what happens is, if you have given some new test point, so suppose your test point is let's say x test is, suppose 2 2, right? So now I wanted to find what is the prediction for y. Is that correct? So what if this data set comes or this data point comes in, what is the prediction for this data point? That is what we wanted to find out. And what does the k nearest neighbor does is, so based on what is the value of k, it will try to predict the uh, try to predict the label for this test point. So where exactly do you think this point will lie? So let's say this was 1 2, so let's say 2 2 will be somewhere here, right? Okay, so how this algorithm works is based on the majority, and suppose you can actually use different instances, but in this course we are actually looking at for the uh, we are actually looking at for the nearest neighbor. So how many nearest neighbors are there? Fine. So suppose you have, if I say that I wanted to find one nearest neighbor, so what will be the prediction of this data point? Is the test data point. So what is the prediction for this? So which is the nearest point from here? X1,
One one.
right? X1 1. So here it is. Oh, okay, okay. You're saying that one, two. Yeah. So that means this one, X1, right? So the nearest point is this. So what will be the prediction for X test? Sorry. So okay. So X test, for X test, the Y prediction will be
-1.
negative class. This is when you have one nearest neighbor. Okay. So if I say later on, I wanted to find, like, if I have uh, four nearest neighbor, so what will be the prediction?
Then it will be a tie, sir.
It will be a tie, right? So that means we don't know. So in the tie case, what should be the prediction? It can either be negative class or it can be a positive class, right? If I have the
Yes.
four nearest neighbor. Okay, suppose if I have one more data point here, let's say this is again another point. I don't know what is the value of this. Let's say this is another data point. If you have during your training, which is, let's say, x6, x5, and there is another data point x6. So now if I say that I wanted to find out using the prediction for by using the six nearest neighbor. So okay, I'll just give the class. So this is positive class, this is positive class. So can you tell me what will be prediction for X test?
+1.
Plus 1.
Plus one, right? Okay. So, but if you understand it visually, what do you think X test should be predicted at? Like, what should be the class related to the X test? What do you think? If you
Minus 1. Minus
minus
1.
1.
it should be a negative class, right? Okay. What about my X test is not here, and let's say X test is somewhere here. What is the prediction for this?
If it is 6, then
If it
again
yeah, yeah, I'm,
plus.
I'm just talking about six nearest neighbor,
Then also it's plus.
right? So what is the problem if you do six nearest, or if you do n, if n in the sense when you I'm saying that if you have n examples in your training data, and if you choose this n nearest neighbors, what it will the what is the issue here with this approach?
Label will always be the majority
So
one.
yeah, so whatever the majority class is there during our training, it will always try to predict the same class irrespective of where the data point, the test data point lies, right? So that means it will not, it possibly will not give you the correct prediction. It will always give the positive class for any test data point, whether it lies here or whether it lies here, or right. So that is the problem with if you have n nearest neighbor. If you have one nearest neighbor, what is the problem? So suppose if you say that, let's say this is the data point, right? So if I just, okay, think about this. Okay, this is not the proper
Mhm.
diagram possibly, but if this is a test point, uh, or maybe I'm just,
Sir, can I ask a question
yes,
about
yes, 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 please, yeah,
sir, it's a question from graded assignment 7, question number 2.
okay, grade assignment 7, huh?
It's on the same topic.
Okay, grade assignment question number 7,
Sir, question number 2.
2, okay, so
No, sir, graded
yeah, yeah,
assignment.
yeah. Question this one, yeah.
Yes, sir. So, sir,
The blue and the red points belong to two different classes. Okay, both of them are a part of the training data set. Blue and red. Okay, the black point at 1 2 also belongs to a training data set, but it is true color is hidden from our view. The black point at 2 2 is a test point. Okay, so this is a test point. This is a train point. How should we recolor that? The black train point if the test point is classified as red without any uncertainty by k nearest classifier with k equals to 4. Okay, so okay, so that is the question, right? So what do you think about? So I know what is this test is prediction. What is the test
sir,
prediction here?
firstly, we have to find the 1 2 point. That is the train
Yeah,
point
yeah,
here.
but if you see the question, what is the question? How should we
Without
recolor?
finding that, without finding the color of that point, how can we decide the test?
Yeah,
Uh,
yeah, yeah,
test
I understand, but it is given in the question that the test point is classified as red with k equals to 4. So I know this is the red class. Okay,
okay.
using the k equals to 4. So k equals to 4, what does that mean? How many okay, what is the four nearest neighbor to this test point, which are, or which are all the nearest neighbors? Possibly
So
this
yes,
one,
all the yeah,
this
the
one,
three,
and this
your
one, right?
three rate points are there.
Yeah, so this, let's say this is the plus sign, right? I think this is the, these are all like 1 2 3 and 4. This might be the uh, four nearest neighbor to this, right?
Yes,
Okay, so now it is already classified. This test point is classified as the red,
right.
red point, right? And
Yes.
now, if it is like that, then what do you think about this point? Then, so
Okay.
generally, what is the k nearest neighbor? Like, how does this prediction happens? Prediction will be the majority of the,
The maximum.
yeah, majority, right? So
Yeah.
majority of this class
Majority.
between these points, right? So whatever the nearest neighbors are there. So what do you think with the certainty that if this was a red color, then definitely by majority it will give me the red, right? If it is a blue,
Yes.
then
Sir, in that case, what will happen?
yeah. So
It will be a
that
tie.
is the, sorry.
It will be a tie if it is blue.
Yeah, it is. If it is a tie, then if yeah, it is a tie, right? So that is correct. And then in that tie situation, it can be a blue data point or it can be a red data point, right? Because then it's a choice of yours, right? Whichever you wanted to classify, that is not a problem. But for sure, what you can say about this? So I think
It'll be red, yes.
red, right? Because there is no, if I wanted a like certainty that this test point is red based on the majority using the k equals to 4, this has to be a red data point, right? That is
Yes.
what it is saying. How should we
Yes, sir. Now
recolor
it
the
is
black?
clear. I have missed that part of that question. Yes.
Yeah,
Thank
right,
you.
no? Yeah, okay.
Yes, sir.
Sir, does K always have to be odd?
No, not required, right? It can be anything. So here in this case, k equals to 4,
Because
right?
if we keep it as even, then there is a chance of a tie. But if it is odd, then there is no chance of a tie, right?
Yeah, then it is not, because then it is not possible, right? To have the tie. Right? That is
So
true.
preferably, should we keep it as
No, no,
always
it is
odd?
not like, it is not
So,
any
sir, by
preference.
convention, we are taking K as odd numbers, right?
Yeah, because it will not give you the tie situation, right? As you
Mm.
said. So it's like if you have the 5, then definitely 2 or 3 will be in the same one class and 2 will be another class. So that will like, uh, you will not be in a dilemma at any point of time, right? So that is the thing. But it is not like you can't take k equals to
It's
4
not
and
a rule, but we try
yeah,
to avoid that situation. So
yeah.
that's yeah.
But that also can lead to your wrong uh, classifications, right? So so how you say that which is the best case, right? So that is the point again, right? So as you are saying that we can have odd, we can have even, or you cannot have n nearest neighbor, because if you have all the data points as your nearest neighbor to try to predict for the test data point, it will always be biased towards whatever, whichever is the maximum class, right? Correct. So these things are there, so that means you need to do some uh, what is it, what is maybe you will have to do uh, some trial and error, or that is actually called as, like in this case we don't do trial and error. What do you do here to find out what is the good choice of k? You will do the cross validation, right? Have you seen the cross validation techniques before this week? I think we have seen.
Yes, 6 week 6 covered.
Yeah, cross validation. What does it do? Whatever your training data set is there.
We will divide it into K fold, and we will train in K minus 1 fold and
Yeah,
validate on the K
right.
left out fold.
Yeah, so there are actually a bunch of cross validation techniques. What we are seeing here is one of the techniques, right? So k fold cross validation. There is one, another one is leave one out cross validation also. So yeah, so all of these things are there. So what you do generally is, uh, uh, in general scenario, you will have the training data set and you will have, let's say, test data set, right? So what you do generally is like you train your model or algorithm during training, and you will test it on the test data set. But to have the confidence in our, or whatever the biasness is there, if it is there in the data set, to avoid that, what you do is you just divide your data set into k folds, right? So let's say it's 1, 2, 3, 4, and 5. In this case, this is 5 fold. You have just you know, yeah, so you just have uh, break down this data set into, let's say, 5 folds. What do you do then? uh, Now for training purpose, what you can do is, for training, or during training, what you do is, you will consider the train set as, let's say, all the data from 1 plus 2 plus 3 plus 4, and the validation set which will act as a test set, uh, will be 5, right? This is the first, let's say, first time you do, and you will find out what is the error, right? So generally, what is our purpose in everything, like in supervised or unsupervised or everything, is to minimize the error, right? So you will find out the error. And what you do next time? Next time you will take 1 plus 2 plus 3 plus 5, all the data in this four folds, and you train your model onto this data. And what you do next, maybe you take this fourth data set. So like, okay, when I say this four means how many data points will be there? If you have n data points in your data set, if I just divide that into 5 folds, how many data points will be there in each of this fold? Like n by 5, right? So it's like 1000 data points are there, so each fold will contain 200, right? Correct? Okay, am I audible? Yeah. Okay. Yeah. So this is the kind of training and validation you do generally, and you will find out the errors, and then you average it out, and then find out the best solution to that. There is another method which is, I think, I don't know where it is taught or not, but there is called so this is like leave one out cross validation. So it is like that, leave one out cross validation. What does this technique do? In this case, you just leave one data point. So here what you did is, you if you have 1000 data points, you just uh, you just uh, divided that data points into 5 folds, like 200 in each fold, and then you will shuffle all these data points, and you will make one set as a test set or validation set, and other as a training, and you try to find out the errors in the predictions. But in leave one out cross validation, what you do is, out of the 1000 data points, you will have 999 data points as your training data points, and one as the test point. And now we'll check the, or not test point, it will be the validation point. Let's say you train on 999 data points, you test on this validation data set which contains only one data point, and like that, how many times you'll have to do? Like, I think 999 times, right? You'll have to do all of this thing again and again, and then you will average out the error and find out the best possible or optimal solution to this problem, whatever the problem is there. So maybe it's a regression problem, maybe it's a classification problem, and all. Like that you do, right? And then after that, you'll use that model to predict for the test data set. So that is generally we do for cross validation. And here, for finding out the choice of k, you do the same. You'll find out which is the so there are certain methods, which is, I think, one of the methods, the popular methods is the elbow method, right? So elbow method, I think it is not taught here, but you should learn it maybe going forward. Once you enter into machine learning practices, maybe you'll need these kind of techniques to fine tune the models, right? So this is one of the important techniques there in k nearest neighbors. Okay, I think that is the broader understanding of whatever our k nearest neighbors is there. What about this decision boundaries? So yeah, when you have k equals to 1, what happens to the decision boundaries? They will become very sensitive to the outliers. And I think, okay, you just learn about this, or maybe understand about uh, this boundaries later on, maybe, because these are also very important. Okay, so what were the issues with the k nearest neighbors? Is like choosing the distance function. Okay, what distance function should I choose? Should I choose the Euclidean distance? Should I choose the Manhattan distance? Should I choose the Mahalanobis distance? Which is the better one? We don't know. That is also one of the problems. And there is, yeah, prediction is computationally expensive. Why it is computationally expensive?
Every time we need to calculate the distance
Calculate,
from
right?
all the points.
Yeah, so whenever any test data point comes in, every time you'll have to calculate the distances of the test point from all the data points, right? And then only we can decide which are the nearest neighbors. So again, it is not of any use, right? So that means we are not learning here. I think that is the simplest one, and these were the problems associated with this k nearest neighbor. That's why we need another method to uh, use for this classification problems. So then the next simple method was decision trees. What does this decision trees do? So you will have the same data set, right? It's a classification data set where I know that each of this data point belongs to some d-dimensional data, and you have each of this labels corresponding to it. Either it is a positive class or a negative class, or sometimes you can say that it's a positive class or class 1, class 0. So only two classes we are actually looking at it right now. So let's say you have these two classes. What you do is uh, any test point comes in, you will ask some questions and it will traverse through the tree, right? So this is what your tree looks like. So at the end of the like end of the tree, you can see these are the labels, right? So these are the predictions based on some questions which are asked here. So whenever any test point comes in, you'll ask some certain questions, and based on the answers, it will traverse, right? So that you'll end to the uh, classification, right? So maybe it will class based on your answers to those questions, and it will classify it into uh, the labels, right? So okay, so I think all of you know what is the basics of this decision tree. The important thing to know about this is what is a impurity, and what do you mean by pure data set, and what do you mean by impure data set. So if I'll give you one example here, you'll have to tell me whether it is a pure one or impure one. So you have, let's say, four features. I'll just say that F1, F2, 3, F4, and you have the label, corresponding label. So each example is like this. So X1 is, let's say, 2, 3, 5, 5. Class is 1, say plus 1. Another example is X2 is. So how much, what is the each vector, uh, okay, what is the dimensions of each vector here for the data point?
4 dimension.
4 dimensions, right? Yeah. Let's say 1, 2, 4, 5. So that plus 1, 3 is 5, 5, 6, 8. Okay. So is this a pure data set or it's impure data set?
Same pure.
Impure, right? Why we are saying that it's impure?
It has both the classes, like
Both the
plus
classes,
one.
right? So when we call it as a pure data set, when either all of these labels will be either plus 1 or minus 1, right? If all the labels corresponding to these data points which are there, if they are of the same nature, maybe the positive class or the negative class, in that case we say that this data set is a pure data set. If it is not the pure data set, let's say, okay, this is not a pure data set, right? So this data set, we call it as impure data set, right? So what does this decision tree does is, uh, okay, so first of all, before understanding the decision tree, how to measure this impurity in this data set. So you have, okay, so initially, let's say, before asking any question, or I'll not say the question possibly. Okay. So how does we uh, measure this impurity is one of
Entropy.
the entropy of this data set. If I say this data set is like this, x1 y1, x2 y2, x3 y3, and x4 y4, right? This is the data set which is given to me. Now each of x1 here is of 4 dimensions, right? Y I is either plus or squares, right? Okay, so the entropy of this data set actually uh, will be found out by using the formula, which is what? Minus P
Log
log
p
of p minus
minus 1 minus p.
p log of sorry minus p, right? This is the formula for but how does it will work on this data set, like the given data set as what is this p here is a fraction of ones, right? Or maybe I can say the positive class. So generally in this case, to understand this, we say that these are all ones, and instead of this, I'm just saying that this negative class I can denote it by zeros, right? So let's say this is like this 0 1. Now fraction of ones is denoted by this p. So how many ones are there in this data set? So it is 2 by 4, right? So there are 2 ones out of the 4 examples which are there. So the entropy for this data set will be, so yeah, okay, if this p is a fraction of ones, then 1 minus p will be what? Fraction of zeros, right? Or another class, right? So in this case, if p is half, then 1 minus p will be uh, again it's half, right? So this, if I just take out this minus sign common, then it will be half log half plus half log, right? That is your entropy. So this is a general formula for entropy, and this entropy function actually looks like what? Like this. It is already there. Right. And this is what it is. And the entropy will be, so here on the y-axis, it's your entropy, right? And on x-axis, it will be what? P, right? Maybe the fraction of ones and fraction. So p, which is fraction of ones. Here, the fraction of ones will be. So this is a pure. Maybe if you have all, if you have the fraction p equals to 1, then all the classes will be positive classes. If you have p equals to 0, then that means it is all the classes will be. So you can see that the entropy for the pure uh, data set, it will be 0, and it will be maximum at 1 by 2. So whatever in between values will be there, it can take it in between values, but the entropy decreases from half to 1. Also it decreases from half to 0. So this is a symmetric function, right? So this is how you find out the entropy. Now the thing is, okay, maybe I'll just show you. Possibly this is
Sir, what is the entropy for that
which one?
example you have taken?
Is this one, right? So how will you write this entropy? Possibly, okay. Uh, Basically, if I just actually if you think this minus sign inside, right? How it will look like? So
So
half
it will turn to
log
be
2,
1.
yeah, log 2 plus half log 2, right? Is that correct? And
Yes.
and okay, what is the value for log 2? If the base is 2, right? So log base 2, if I am just taking the base 2, then it will become 1, right? Then this half log to the base 2 will be 1, right? So then it will become half plus half equal to 1. But if the base to the base is yes e, then what happens? Or any other base apart from 2, then it will not turn out to be 1, right? It will have some other values, correct?
But sir, you said that it will, if the impurity is high, then we will end up with 0.5, right?
End up with zero point 0.5. Okay, what will be the values of entropy? Entropy values will be here, right, on y-axis. I don't
Oh,
know what are
okay.
the values, right? It can be any number, right? It cannot be between 0 and 1. Is
Okay.
that correct? It can be anything. The only, this is the
Okay.
fraction. On the x-axis, we have the fractions. Fractions at, if the fraction of ones is half, that time entropy is maximum. That I can be sure of. But
Okay,
what
sir.
is the
Thank
value
you.
of it? We don't know, right? So basically, it will be if I just do it properly, then I can actually take log 2 common, and then it will be like 1, right? So this value is log 2. If the base is 2, then this will become 1. If the base is e, then you will have some other value. If the base is 10, then it will be some different value, right? So it depends like how you are taking these logs. But we cannot say that entropy will be 1 when the fraction of ones is half, right? Like it's like purely impure data set, right? Okay. This is
So
clear.
we can say that if it is taking 0 or 1, p is taking 0 or 1, then the entropy will be 0.
Zero, yeah, definitely zero. And then at that point, it doesn't matter what is the base of the log is, right? So how can we say that? Let's say if p is 1, right? Let's say p equals to 1. In this case, what will be the entropy? We'll try to find it out. So what is the formula for entropy at any data set? Is like
It will
minus of
become 0.
p log p plus 1 minus p log of 1 minus p, right? This is the formula. When p is equals to 1, what happens? Uh, this
Log
will
1.
become 0, right? This part will become 0. So this will be minus of 1. So basically it's log 1. So log 1 to any base, right? Generally this value becomes
Yes, sir, 0.
0, right? And if you have p equals to 0, in that case log 0 will be so this will become anyway. So we, by convention, we say that log of 0 also will be equal to 0. And anyway, if you are multiplying 0 with any other value, this multiplication will be equal to 0 anyway. So 1 minus p will be 1 log of 1. So again it is 0. Okay, that we are sure about. Like when you have fraction of ones as 0 or fraction of ones as 1, in that case definitely we are sure about that entropy will be 0. But when it is any other number, we'll have to calculate it is not 0, but we do not know the maximum value is also 1, right? It depends. Okay, fine. I think that was it here. uh, Okay, I wanted to show you something else, right? Sentry. Okay, this is actually about the decision boundary or decision surface. How it is looking like. This okay. So what does that mean actually? How to partition this space, right? How how you ask the questions and how it will grow the tree. That is the showing. I'll just see that. Okay. So I think this thing is not there. The pruning is not there, but we'll try to understand what is pruning is. Maybe I'll just okay. I'll just go through once. It is what is it? There are so many things actually. This okay. So all of you know how to grow the tree. Uh, so this was the data set given to us, right? How many classes you can see here? 2 classes. Is this a impure data set or a pure data set by looking at this uh, training data? What do you think? It's impure one, right? Because you have 2 classes. Definitely you have some data points which belongs to one class, let's say red class, and some points belongs to the green class. So that means you have uh, data points related to both the classes. That means it's not definitely a. So first question you asked is x2. Okay, how many variables you are having here, or input variables or attributes? How many you are having here? Two. One on the x-axis, one on the y-axis, right? So if you ask first question where x2 is less than 5.5, so it will create a line here on the x2 axis. Let's say you have x1 here, here it is x2, and x2 is less than 0.5, in that case we are saying that this belongs to okay, if the answer is yes, then what do you say? If it is less than 5.5, it belongs to class 0, and if it is no, then it belongs to class 1, right? That we are saying here. What does that mean? Your partitioned this space here, right? So whichever we are saying that belongs to this, it's class 1, and now belongs upside it is class 0. What next thing you are asking? When x1 is less than 5.5, in that case when you are saying that if the answer to this question is yes, so that means this space, if this is a 0 class and this is a 1 class, right? The same thing, if the answer to the first question, which is x2 is less than 5.5, was no, that means all the data points we are looking at which are above x2, above this 5.5, that means this region. And the next question we ask is if x1 is less than 5.5, the same kind of question we have asked here, and the answer is here. If it is yes, then we say 1, and if it is no, then we say 0. So are you able to understand the difference here? This was the same question. If the answer to this question yes is, then we ask another question which is x1 is less than 5.5, and if the answer to this question is yes, in this case we say 0, and if the answer to this question is no, we say 1. But for the same kind of question which is asked here, if it is yes, the answer to this question is yes, then it belongs to the class 1, and if it is no, then it belongs to the class 0. So is it the correct questions we have asked here? What do you think? Yes, right?
Yes, sir.
Yeah. So at the end of this question or at this part, uh, do the data set. What is the data set here, or what are the data points which are lying in this data set? You can just tell me like whether okay, this is you can call it as left top corner, this is right top corner, this is right bottom corner, and this is left bottom corner. So what is, which is this representing?
Left bottom corner.
x2 less than 0.5, and okay, this part, right? All this, so is now the data set is all the data points which are here. So is this a pure data set now,
Yes.
right? So if you see actually, so all the partitions which have happened here, each of the partitions, actually they are the pure ones, right? So what does that mean? The entropy is
0.
0 for all of them, right? Like separately, it's not like entirely, but the separate classes it is 0. And at the start of this uh, tree, what was the entropy here? Was that 0 or was it uh, uh, different than 0?
Different.
Right, it was not the 0, it was say, some different number, but it was some positive number, right? So we know that entropy, the minimum value of the entropy can be 0, and maximum it can be anything, right? So any value, let's say. uh, the goal here in the decision tree algorithm is to achieve the minimum entropy, right? And how minimum we can go is 0. So after asking each of the question, if you are getting the lower entropy than the previous one, uh, are we going into the correct direction?
Yeah.
Yes, right. So initially we had some entropy, like let's say we had some, I'm just getting some number. Let's say we have the entropy here at which was 5. Then we have asked one question which is x2 is less than 5.5. Now what happened here? When I have asked this question x2 is less than 5.5, then I have just broken down this data set into two pieces. So one piece is above this line and another is below this line. So we'll calculate the entropy for this separately, we'll calculate the entropy for this separately. Now we check that whether the entropy is reduced from the previous one, right? And if it is lower than the previous one, then what we say is that we are actually going into the correct direction. Is that correct? Right, because we need to find out, right, whether we are actually going into the correct direction or not. If the entropy remains the same, or it does not change, then that means we are not actually going into this same direction. So what you do generally is, so we need some metric to say that whether whenever you are traversing through a tree, uh, that we are actually traversing into a correct direction. And how to the important thing about this decision tree is the entropy, right? We actually find out the entropies. So our goal is to find the minimum entropy, right? Minimum entropy at the end of the tree, right? So this is our goal. But how we say that we are actually asking the correct set of questions and we are actually moving into the correct direction is to find out whether after each of the question we are getting the minimum entropy or not. And that actually is fine, like we can find it out by using the term which is called as the information gain. There is another term called Gini index, right? So that is also there, and it is also based on the entropy only, but that is not that formula is not in our syllabus, but you can actually so if you wanted to learn, you can learn it separately. So information gain is what you do is you will find out the entropy initially, right, let's say at that point. And what you do then, so what is the so you are saying that initially we had some entropy 5, then you ask some question and you had the two answers, let's say one is yes and another is no. And uh, you, let's say you had 100 data points initially. Now because of that question, let's say 60 data points goes into this side, 40 goes to that side. The entropy corresponding this to this 100 data set was, let's say, 5. And now you calculate the entropy after asking one question. You have actually partitioned that data set into two uh, maybe two sets or something, right? So let's say one of the set contains 60 points, another set contains 40 points. uh, let's say the entropy corresponding to this is, let's say, 3, and entropy corresponding to this is, let's say, 2. What do you think? Did you ask the right question here? Was the question asked here was the right one or not? How will you say that whether it is the right question or not?
Yeah, it was the right question because in either cases we've reduced the entropy.
Okay, so okay, so that means, okay, there is one term which is called as the information gain. What is that information gain? Let's say this is capital D. I'll say this as DS, right? DS contain how many data points? 60, and D no contains 40. So information gain says its entropy at this point minus what? Uh, minus of, or okay, minus of, like, gamma times entropy of ds. I think I'm writing the correct formula. I'll check it later on. Okay. Plus 1 minus gamma times entropy of d no, right? Correct? Now just tell me, oh, and okay, what is the gamma here? Gamma is actually, okay, gamma gives me the maybe the fraction of, yes, right? So uh,
Fraction of data points coming into the this ds
yeah.
divided by mod of
So this is cardinality actually. Mod means like
yeah, yes, sir,
cardinality.
yes, sir, sorry.
So basically it's 60 divided by 100, right? Which is zero point 0.6, correct? Initially we had 100 data points, and now in the S it is, so basically actually it's like it gives some fraction, like how many fraction of data points goes to that side, and we just like multiplied with the, so what I said is initially my entropy was 5, right? Minus zero point 0.6 times 3 plus zero point 4 times 2. So this is 1.8 plus 0.8 and 5 minus, right? So how much it is? 2.6, which is
2.4.
2.4, right? So that is your information gain. That means, okay, basically you can see here is that the entropy is reduced, right, and you have gained something. So information gain, uh, okay, what should be the value of information gain? Should it be 0 or should it be some positive quantity? If I wanted to check whether we are going into the correct direction, or whatever set of questions you have asked, they are the correct
Should
ones,
be positive.
it should be positive. If the information gain is 0, what does that mean? Are we learning anything or we are not learning anything?
We are ending up with 2 leaves with the same classification as the parent node.
Right, so that means we are not actually learning that, right? So that is the case. So when we have asked this when we have found out, so what do you think about this? Possibly we are actually getting something out of it right now. We don't know, I will have to calculate anyway, but yeah, I think it is there, because at the end of this is sure, is for sure, right? If you are asked this set of questions, now I can say that, okay, sorry, this is the tree. Now if I can say that definitely we have gained something. So what should be the information gain uh, at this node, let's say, or after this question? It will be a positive one, right? So information gain should be positive, right? And uh, what about the entropies at like here? The entropies will be, I think here they all will be 0, right, at this point, this point, this point, this point, this point, because now that
Yeah,
becomes your
everything will be 0.
because your data set become like pure, right, for each of that case, correct? Any doubts here?
No, sir.
No, right? Okay. Now, okay, these are the decision boundaries. Let's say, because these are the positive classes, and yeah, it is like reasonable to understand. So you have 4 regions, 4 leaves. To get it this, I think there are certain questions which are dependent on this. Okay, I think it is the same set of same decision tree. Or sorry, same data set, but we have used some different questions, right? And if I use different questions, you can have 7 regions and 7 leaves. What happens here now? This is one case, and this was another case. Uh, this is another case, right? There's 4 regions, 4 leaves, uh, and this was is the same data set, right? But because we have asked some other questions, this has given me this kind of decision surface or decision boundaries. So what is happening here? So is it overfitting or is it not, or is it trying? If you ask these kind of questions, is it trying to uh, overfit this data set? What do you think about it? It's not. I think because of this outlier, it is trying to uh, get it the right. So if you see the difference between the first data set and another data set, I think there is an outlier here. So I'll go back. Sorry, I'll have to. Okay, so this was the data set initially, right? You just look at all these data points. So here, these are all greens, these are all greens, these are all reds, and this was the perfect one that we are able to, classify that data set into 2 classes very clearly. But if you have the data set like this was the same data set. What was the issue here? There is one outlier here, right? Now, because of this outlier, we'll have to ask more number of questions, and because of that, what happens is we are trying to overfit this data set by asking so many number of questions. So that means now we are trying to overfit the data, and now the decision boundary becomes little bit complicated, right? But is it required there? Uh, can I can I get the same data set using or uh, okay? So what is happening here at the end of end load nodes or the leaf nodes at the end? This data set becomes pure, right? Correct. So the entropies at each of these nodes here, 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 it is actually becomes zero, right? But is it desirable case for us? But if I look at this data set, what I can understand is maybe if I ask the similar set of questions which were asked in the previous problem, that was enough, right? I don't need these many questions to perfectly fit the data. If I can actually uh, gain something out of the uh, previous question, but the entropies might not be zero at the end of the tree. So this what is happening here is this is the outlier, and we are actually trying to fit that outlier. So what to do in this case? So we'll have to stop at certain point of nodes, because see these were the very small trees, but it is possible that you can actually grow a tree, a very big kind of tree. And okay, what is the depth in this case here? How to say that? What is the depth? Is it taught there? Like, what is the depth of the tree? No,
5, 4.
4.
4, right? 4 or 5?
4.
4, right? So this is the depth of the tree. So is it possible to is it possible to stop before reaching to the end of the tree, right? Or do we need to go to the end of the tree? That is the problem, and or that is the thing which we have to understand. There are certain criteria to do that, which are actually called as a pruning, or there are actually pre-pruning, post-pruning, all these things will be there. But let's say you'll have to see the stopping criteria. That is, general criteria is when the leaves become pure, will stop, right? So that means it will try to overfit the data set until all whatever the final leaf nodes will be there, they are become the entropies at that point will become zero. Then only will stop generally. But is it possible to get the so if you are okay, what are these criteria? We'll try to see is pre-pruning and post-pruning. Okay, is not required. Post-pruning is not required. We'll understand only pre-pruning. What is it? At least we can do minimum samples at leaf node. We can decide on the maximum depth, and which is this minimum decrease in the impurity. So okay, what is the first criteria says to me minimum samples at leaf node? What does that mean? Okay, we are saying that we should stop growing the tree by these three methods, right? And that we decide earlier before starting to grow the tree, right? So first thing is minimum samples at the leaf node. So we decide that if at any node, if the number of samples will become less than this threshold, what does that mean? I'll try to tell you. So let's say you have a data set with 100 data points initially, right? What I'm saying is, if at any node, if the data set becomes becomes less than, let's say, 20, then we'll stop growing the tree. Okay, if that is the condition. Suppose we'll start with some question 1, and you had data set at this point which contains 100 data points, suppose say 100, and here you have two questions, yes and no. Here at this point you have data set which is Okay, let's say ds is 60, dno definitely will be equal to 40. Then we ask another question, uh, again, which is having, let's say, yes no answers, and here again you have uh, the numbers as, let's say, 15, and here you have how many, 45, right? Similarly here, if you have two questions and you have one answer here, let's say, again here it is, here it is yes no, if you have 25 and 50. So what do you do here? Actually, see, and what I'm saying is the entropy at this point is not equal to 0. So entropy or at all these points are not actually equal to 0. Okay. But what we said already, we have decided that if the data set, the number of uh, values in the sample or this data set, if they goes less than 20 at any node, we will not the grow the, or will not ask the next questions, right? So that means what we are doing is we are not growing the tree after this point of time. We'll stop at this point of time, even if the entropy we are not getting it 0. That means even if we are not getting the pure nodes, we are stopping at this point. That is one of the techniques to stop the tree. What does that mean? We are not trying to overfit the data. It is one of the technique. Another is what? Getting a maximum depth. So in this case, we had a tree with the depth as 4, right? But what we decided is we'll not go uh, below 3, right? So now what happens is, where we'll stop? We'll not ask the question after this, right? Or we are not going to ask this question. Is that correct? We stop at this point only. Whatever the impurity we will be having, we'll stop at this point. Another case will be minimum decrease in the impurity. So suppose the information gain we are getting at any nodes, if that becomes significantly less, at that point we'll stop, right? So I hope you understand these 3 points why we are when we are stopping, and this is what we are actually deciding uh, very early, right? Before starting to grow the tree. So these are the three stopping criterias, which actually we are actually getting these criterias before starting to grow the tree, and that's why it is called the pre-pruning. Pruning is basically is like we are stopping at certain point. Pre-pruning means like we are deciding it before starting to grow the tree. Similarly, there will be some post-pruning criteria. That means once you start uh, growing the tree, at after once it is done, right, then we just find it out, shall we stop at this point or not. That is not here in the syllabus, so I'm not going into that details. But I think sir has mentioned about maximum depth in the lectures, right? We actually can stop growing the tree. I think sir has given the example of that doctor, right? If you wanted to show some 100 trees to the doctor, he might not uh, use that information to understand or diagnosis the patient. But if you give the some 4 or 5 questions, then that will be a good thing for him, right? So that is one of the uh, uh, criteria I think he has mentioned, but he didn't say that it's pre-pruning or post-pruning, right?
So, how does one decide this threshold? Is it like a domain expert thing?
Yes, it's a yeah, you can say that it's a domain expert thing, or you can actually, so if you just okay, again, what are these things? So I said already, right? There are parameters. There are,
Hyperparameters.
what are these three?
Hyperparameters?
Yes, right. So and how you choose the hyperparameters?
Hit and trial or cross.
And yeah, so validation you do, right? And that is the thing. So you just decided based on the cross validation, understand? So whatever the hyperparameters are there, you generally decide it based on the validation. So you just do like different validations, and then you decide, okay, I'll have to stop it here. Correct, right?
Yeah.
Okay, so generally hyperparameters we don't learn it through training, those are actually found out by using the validation techniques. Okay, I hope this is fine. Do you want me to solve any question on information gain or entropy? If you want, you can just let me know. I'll solve it. That. Like, do you want any do question on this topic? It is in the mock. Okay, you wanted me to solve in mock, right? Okay, fine. Mock test. Apart from that, I think it's this week is like basically, I think it's very simple week. So is to mock. What is the question number? How to calculate IG? IG is information here when depth is 2. Huh? Where? Okay, in this mock you're saying. Okay. Where is that question? Data. This one?
Yes, sir. This one. Yes, sir.
A decision stump is a decision tree that has exactly one question at the parent node, which then splits into two prediction nodes. Okay. Consider a decision stump for a binary classification problem that has 500 data points at the parent node. So where you'll have the 500 data points here, out of which 200 goes to the left one, and definitely 300 will go to this side. Number of data points that belongs to class 1 in the parent node is 300. Number of data points that belong to class 1 in the left child is 50. The labels are 1, 0. Log to 4. And what is the label assigned to the left child? Okay. So yeah, I will try to understand this. What is it given to me here? One is
Sir,
parent. Yeah.
500.
in the exam, will you be specify about this? What log to the base?
Yeah. Definitely. Yeah. The values will be given to you. So, so generally, what you is like you'll given to you that the values which are required, right? So you will give log to the base 5. Suppose some value is given to you, and there is maybe log. Uh, so you'll get like bunch of values. You'll have to find out which are relevant to you. So you understand it, right? You
Okay,
don't need to calculate using the calculator. The values will be
okay,
available there.
sure. Thank you.
Okay, so you have 500 data points here, and among which uh, what is what is it said? The number of data points that belong to class 1 is 300. So can I say that this is kind of like that, 300 and 200, which is class 1, class 0. Is it fine? Okay, and what is next part? The number of data points that belong to class 1 in the left child is 50. Okay. First thing, I think it goes to the left child. This is the left one. Is the right one. Left child, how many data points are there? So I'll say that, let's say DL. DL contains 200
200.
data points. Among those 200, how many are plus ones in 50? And the remaining 150 will be 0. Is that correct?
Yes, sir.
Okay. And what is the label assigned to the left child? That is what the question is, I guess. Okay. So let try to understand first of all how many data points will be there in D, right? So 200 goes to here. So that means 300 will goes to the right side. Is that correct? No issues with that? Any issues here?
No, sir.
No. So, okay, we'll have to decide how many positive class data points will be there among these 300. So, how many total, positive class data points were there in the original data set? 300, right? Out of this 300, 50 goes to this side. So what do you think, how many should go to this side, positive data points? The remaining ones, right? Can I say that they will be equals to 250? And definitely the remaining zeros, so they will be 50 here. You can just now you can just sum up all these things. So 250 positive, or one class, and 50 one class, so it is 300 of the class 1. Initially there were 200 data points which are belonging to class 0, among which 150 goes to the left side, and then the 50 goes to the right side. Now this is the data set we are looking at it. The question is, what is the label assigned to the left child? Okay, what does that mean? Hmm? Any other questions are there? What is the entropy of the parent? What is the entropy of the left child? And what is the entropy of the right child? What is the information gain? Okay, these are the questions we need to ask. We need to answer. Okay, let us try to. Oh, sorry, what is happening here? Okay, we'll come to this question. What about the left child uh, label? We'll find out what are the entropies first place, right? So I think that is the simple thing which we can do here. Okay, what is the entropy at the parent node? Entropy, let's say at the parent node, I'm just denoting P as the parent, right? L for the left child and R for the right child. So what is the entropy at parent? It will be minus of P log P plus 1 minus P log of 1 minus P. Correct? What is the P? P is the proportion of ones. So how many ones are there in the data set at the parent node? It is 300. So it is 300 divided by total, so which is 500. That means it is 3 by 5. Or if you wanted to like simplify it, it will become 0.8, right? So yeah, minus of 3 by 5 log of 3 by 5 plus 2 by 5 log of 2 by 5, and all of them are with the base 2. So this is the entropy at the parent node. You can calculate it maybe later on. What is the entropy at the left child? Entropy left will be minus of what is the proportion here for ones? Let's say PL will be 50 by 200, PR will be 250 by 300. So basically this will become 1/4, right? This is 3/4. No, 5/6. 5/6. Okay, right. So entropy at the left side will be 1 by 4 log of 1 by 4 plus 3 by 4 log of 3 by 4. Again, the base will be 2 here. Similarly, the entropy in the right child will be minus of 5 by 6 log to the base 2, 5 by 6 plus 5 by 6, not 5 by 6, it's 1 by 6 because it is 1 minus p log to the base 2, 5 by 6. These are the entropy. Yeah.
Was the base given in the question?
What is it?
Was the base given in the question for log?
Yeah, I think it is given. No, so it is said that here, not for the calculation, use log 2.
It will always
Log
be
to the
given,
base.
right?
Yeah, it should be given, right? Otherwise, you will not be able to, like, how will you know, right?
Mhm.
You should use. So it has to be given.
Yeah.
Okay, so then these are the entropies at the parent node, left child node, and the right child node, right? Now, what we wanted to find out whether the information gain. So for to calculate the information gain, what is needed here? What or generally what you need is there is another parameter which is called gamma, right? So gamma is what? ds by d. So this is the cardinality of ds, right? What does that mean? Let's say how many data points are there in the, let's say now we are considering in the left child node, right? So in that case it will be 200 data points here, 200 divided by how many total were there initially. So after, when we ask that question at the parent node, if the data set actually partitioned into the two uh, sets, so what is the data points in the, I'm assuming that the left one is the answer to the question at the parent node is yes. So assuming that, it will be 200 by 500, which is 2 by 5. So information gain basically will be entropy at the parent node minus 2 by 5 times the entropy at the left node plus 3 by 5 the entropy of the right node. Is that correct? That should be the answer to the information gain. I hope this is fine. I'm not calculating it, but I think that's fine, right? Okay, so the gamma value, it doesn't matter. If you can take like 3 by 5 also, it will not matter, right? So because it will give you the same answer for the information gain anyway. So this is the value for gamma. The value for gamma. This is the value for proportion of ones in the right side. This is the value for proportion of ones in the left side, and this is proportion of ones in the maybe the parent node side, right? So how many ones are there in the at the starting? This is how many ones are there in the left side node, which is this one, PL, PR. This is your, okay, P will be 300 divided by 500. I can say that PP, and this is the gamma. Okay, I think you can be able to solve it now. I have answered, I think, all the other questions which are there. What is the entropy of the parent? What is the entropy of the left child? What is the entropy of the right child? And what is the information gain corresponding to the question at the parent node? Fine. What about this now? What is the label assigned to the left child? What does that mean? Okay, so basically what will be the label, right? So and how will you decide the label? uh, Again, it is like whichever is having the highest, like you can just understand, right? It's a kind of a majority, right? So you can directly say that it might be a 0, right? Because 150 data points actually correspond to 0. So can I say that these are 0 point or 0 label assigned to the left based on the majority only? And what will be the label assigned to the right side question? So it will be 1 because it is having the majority of ones there. I hope this is fine. Okay, are you guys listening?
Yes, sir.
Okay, done. Fine. I think this is fine. Any other questions on this decision tree? If you have any doubts, like you don't understand any concept or anything in the lectures, because or in the decision surface, how this decision surface works, or maybe decision boundaries in the KNN or in the decision trees. If not, then we'll move to the next topic, which is naive Bayes. Right? I will just check once this how to calculate. Okay, this is done, right? Okay, fine. Naive Bayes. Yeah.
This is for depth one, right, sir?
Which one? The question which you have asked right now, right? Yeah.
Yeah.
Yeah. Yeah. Depth one only. Yes.
Yeah, if it has depth two, how will the calculation be?
Okay. So it will be the same. See, I'll tell you how to do that. Suppose I'll just take a simple example again. Maybe I'm writing this as a Q1. There is another, let's say, Q2 here. There is Q3 here, and then we have one more, right? So let's say these were the nodes. Right now, I'm not going the tree beyond that. Okay, then what is the entropy here? Let's say it will be a total data set, right? Capital D. Now it will partition into two, D1 and D2, right? After that also, this D1 actually, let's say that, what is, maybe can I say that it is, let's say DS. Okay, but then I'll say D11, D12, fine. And here it will be D21 and D22. Okay, what does that mean? So initially we had 500 data points here. Here when it is partitioned, it becomes 300 here and 200 this side. Now here, let's say after the partitioning, we had let's say 200, and here it's 100. Here it is 100, and here it is 100. Suppose we're just assuming it some. And in this 500, we have, let's say, 300 positives, 200 zeros. Okay, here you have uh, 300, right? So let's say I'm having 101, and okay, then it will become 200 ones, and let's say 100 zeros. So definitely you will remain with 100 ones here and 100 zeros here, right? Okay, now I'm saying that in this D21, all 100 are ones, all 100 are zeros. Similarly, what I'm saying here is, let's say we have not reached it yet, but suppose you have D21 will contain how many hundreds? Oh, sorry, how many positive class is, suppose 100 positive, negative, and here it's 100 positive. That's fine.
Yes, sir.
Okay. Sorry, I think it's wrong. One. Now, how will you calculate the information gain at this parent node? Okay. If that is the question, what do you need to find out? You'll find out the entropy at this point, right? You'll find out the entropy at this point, and then you calculate the information gain for this node. But what is the information gain at Q2? Then you just find out the entropy at this point, entropy at this point, and then you can find out the information gain, because you already have this entropy. You can actually find it out, and then you find out the information gain at this Q2. The total information gain will be what then? This plus
Summation
this,
of all.
yeah, right? So this plus this, right? So this information gain plus this information gain, right? Is that fine? Okay, how to find out the information gain at this point? So what is the entropy at Q2? Q2 will be minus of 2 by 3 log 2 by 3 plus 1 by 3 log 1 by 3. Why? Can you tell me why? Because what is
Yes,
this?
sir. It has 200 ones and 100
Yes.
zeros.
So this is the proportion of ones in the data set. So in the proportion proportion of ones in this data set is, there are like 200 ones, and total number of points in the data set is 300. So entropy at Q2 will be this part. Then what is the entropy at, let's say, D11? So entropy at D11 will be minus of, so how many ones are there in this case? 100. So 100 by, so 1 by 2, total data points will be 200. So 1 by 2. So the proportion of ones here is 100 by 200, which is 1 by 2. So here the entropy at this point is 1 by 2 log of 1 by 2 plus
1 by 2 log of 1 by 2.
right, 1 by 2 log of 1 by 2. Okay. Similarly, entropy at D12. D12, what is uh, what is the value of proportion here? 1, because there are, how many ones are there in this data set? 100.
100.
And out of how many data points?
100.
100. So 100 by 100 is 1. So entropy at D2 will be 0, because anyway it's become a pure node, right? And if you wanted to find out whether it is correct or not, you can just say that minus of 1 log 1 plus 0 log 0, right? And by convention we are saying that log of 0 is 0, so 0 into 0 is anyway 0. Log of 1 we know it is 0, so it is 0. So totally this entropy at this point will be 0. Okay, now what is the information gain at this point q2? So that will be information gain equals to entropy at q2 minus gamma. Gamma is what? Gamma is number of so in this case, let's say it will be d11. How many data points are there in d11 divided by total data points in, let's say, q2, or maybe I can say d1. So that will be 200 out of 300. You can actually calculate the gamma here also. It will become then 100 divided by how many? 300, right? But or then this will become 1 minus gamma. But okay, whatever you can do, you can do. It's not a problem, because then you'll have to anyway apply. So I'm just writing down this gamma will be 2 by 3 into entropy of d11 plus 1 by 3 entropy of d12. Okay, and we know this entropy of d12 is 0. So this is basically entropy of q2 minus this. So this is information gain at q2, right? And this, if this is a positive quantity, that means we are actually going into the correct direction. I hope that is okay.
Sir, if the question is to find the information gain in total,
Then it will be this plus this, no? This one plus this one. In total will be like, then okay, then you will have to find this one, this one, this one, and this, like every side, and then you can actually add it up.
so you mean to say the information gain can only be found
At the
if
node, at
at,
that point.
only at one point, like
Yeah,
one
yeah,
node?
yeah.
Okay.
Then only see what we are saying, that whether this is just kind of like that, right? Like if I am saying that this question is there, I'm saying that whether this is correct or not. Okay, now I am able to divide it now into two answers, right? So or maybe two classes or two answers. So that point, what I have gained it, right? So next point, it will be a different question, and what I have gained by asking that question, right? So what I have gained by asking this question, what I have gained by asking this question, what I have gained by asking this question. So it will be like separate, at separate question, what I have gained it, right? So these are all uh, like that only, right? So that is the case. Okay, so every time this information gain is positive, that means actually you are asking the right set of questions. If that becomes 0, then you didn't actually do well, right? That means that question is not well enough to ask, because you are not able to decrease the entropy. Our goal is to reduce the entropy. If it is equal to 0, that means whatever the entropy was there initially in the data set, I am actually not able to reduce it. Okay, right? Yes or no?
Yes, sir. Thank you.
Yeah. Okay, so shall we go to the knife base? Okay, I'll just skip off the parts, some parts here. Okay, you if you need it, I'll share this slides also with you. Uh, Before diving into this part, maybe I'll just go through the lecture slides. Okay, there are two types of modeling. I hope you understand this part, the generative models and the discriminative models. What is the difference between a generative and, let's say we were talking about, let's say we talk about the text related to the text thing, right? So what does this means? If x is a x is a feature which is, it's a I'll take the same example which is sir has taken, the spam mail or non non spam email. X will be a feature which is like a mail, right? Which is let's say any mail is there, and the corresponding label whether it is a spam email or non spam email. What does this gives me? This probability, basically it's a joint density, right? Joint density between the two features, or feature and a label. So given that, and this is what this gives me, given if I know uh, this is a text, given that this is a text, what is the probability that this is a spam email, right? And here in the generative models it is like, we know the pair of a spam, pair of a email content and its label, what is the probability of getting that pair? That is the understanding of the generative models. Okay, maybe I think this is not here. You understand the difference, right? Or otherwise I'll just uh, do you understand this part? Can anybody explain to me what is this, what is this means, this case, generative case? Anyone?
So there is a mail with words like "Hello, how are you?"
Huh.
and it is also classified as spam. So the probability there is 0.01. It's a giant probability.
Right.
Yeah.
Yeah. So you have already an email and its label. So what is the probability that this kind of combination will exist, right? In the mail. If this kind of combination is there, then that what is the probability associated with that? It is given to us. Is that correct? And what is this vector shows me here? The dictionary, right? Entire dictionary of words are actually, uh, I think, okay. So this dictionary actually, or this vector actually, is useful to get this kind of probabilities, right? I think this is fine. This generative story and all. I think, shall I go through all of this, or number of? Okay, this is important question. When to find out the number of models? But okay, I'll just go through this first. The naive Bayes theorem. I'll try to. This example is better or not? Okay, this is a good example, right? Text classification. So you have this kind of data set, right? You have the features X, you have the corresponding labels Y. What is this first example given to me? Like some numbers, right? Let's say 2, 4, 8, 6, 7. If this kind of text I can see in the mail, uh, okay, this is the training data. Okay, so if this kind of uh, 2, 4, 8, 6, 7, if I get this kind of text, the label corresponding to it is 0. 60142, the label corresponding to it is 0. 840613 is 0, and like that. If I know if this kind of content is there, like on the left side, which is the feature, I know what exactly the labels associated with that. But how to mathematically model this situation, right? That is our task. So what do you think entire dictionary of will contain, like what how many words it will contain in the dictionary? So I'm just considering this as the one word, right? So 2 is one word, 4 is another word, 8 is another word. So what do you think that these features are generated using what kind of dictionary? How many words will be there in the dictionary? Can anyone says, like, tell me? So 2 is one word, 4 is another word, 8 is another word, 6 is another word. So what do you think that total number of words are there in a dictionary so that we can create this kind of sentences? So let's say 2, 4, 8, 6, 7 is one of the sentence. Uh, can I say that there are 10, uh, 10 words in the dictionary?
Yes, sir.
Right? Which are those 10 words? Maybe 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Right? 10, or I think it will be 11, or oh, sorry, not 9 and 10. Sorry, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. This 10 will be the words. By using the combinations of these words, we are able to generate these features, right? So the first example or first feature is or first example, let's say 24867 is actually coming from the dictionary, right? Which contains these 10 words like 0, 1, 2, 3, 4, 5, 6, 7. And if I see this kind of combination like 24867, the corresponding label is 0. So it is saying like this: if you have a email which has this hello, how are you, I know the corresponding label to this word, right? Is it looking like the same here? I think so, yes, right? So what we are saying is, uh, we are labeling, so whenever we see, uh, we can say that it is a coin. So each word is a coin. It will have uh, uh, like what will be there on the opposite sides of the coin. It will either have 1 or it will either have 0. So when that word will occur in the sentence, so this is a sentence, let's say, if the word will occur in the sentence, what we are saying is, that word will have, or it will show as 1. And if it is not occur in the sentence, uh, it will see, we can see it as a 0. So I'll try to show you the dictionary. Let us say this is a dictionary. It will contain these words: 1, 2, 3, 4, 5, 6, okay, 7, 8, 9, and sorry, not 9 and 10, and 0. Fine. These 10 words are there in the dictionary. Okay. What I'm saying is, each of this we can consider it as a coin. Okay. So let's say it will have head or tail, right? So can I say that it will have 1 or 0? Again, it will have this also. This coin will also have one on one side, and uh, other on, like that. And every will have every word will have this, or every word we are thinking it as a coin, it will have 1 or it will have 0. Now, in an email, let's say you have this thing, 6, 5, 4, and let's say 2. And if I wanted, because I wanted a fixed size of vector for each of the feature or each of the example. Let's say this is one example, x1. X1 is the example which contains this sentence. What we can do is, we can have each, we should have the fixed size of vector. So can I say that x1 will be equal to this feature, or this vector? It will have, let's say, uh, it will have, what is this, we have started with this vector, right? So this was having, say, 1, 2, 3, 4, 5, 6, 7. Okay, I'm sorry, I think, okay, I'll just write down only the 8. Or can I just write down the numbers instead of writing out? You can understand it, right? So it is like one,
Yes.
2, 3, 4, 5, 6, 7, 8, 9, and 0. So what is appeared in x1? Do 1 appear? No, right? So it will, this coin will say the value as 0. Is 2 is there? Yes, 2 is there. So it will say as 1. 3 is there? No. 4 is there? Yes. So it will, because 4 is there, so it will say 1. 5 is there? 1. 6 is there? 1. 0, 0, 0 and 0. So this vector x1 is 0, 1, 0, 1, 1, 1, 0, 0, 0. And what is the probability of x1 and y1, right? So that is, let's say, 0.01. So this is the probability that this feature is there, and let's say corresponding label was y1 is 0. So when we are saying that when I see this vector and the corresponding label equal to 0, the probability associated with this is 0.01, which is actually a joint density. But okay, let us try to see this. So 713, how it will look like? 1, since it is started with 1, so 1, 2, 3 and 7, this will be the vectors. So we are actually getting these kind of vectors here and their corresponding labels. So each of the x will be what? How many dimensional feature it is? 10, right? Correct. So what is the length? What is the length of this vector generally is? It is the length of the dictionary, right? So how many words there can be in a dictionary? Based on that, actually we are saying that this is a vector, this is a feature vector. So each word in the dictionary, we are actually thinking it as a feature, and each feature will have how many values? Or how many categories each feature will have? Okay, so
2 categories.
yes, yes. So these are all features, right? Okay. And each of f1 is actually, so each of f5 is actually 2 categories, either 0 or 1, right? Uh, and then we are actually generating this examples, right? So each of this feature will have, so each xi is what? A data point. So each xi will look like how it's a, okay, it belongs to which dimension? 10
10.
dimensional feature, right? And each of these feature is having actually 2 categories. So whatever it appears, it will, like, you, that means what you are doing here is you are actually tossing a coin and okay, I'm just talking about the naive Bayes theorem, right? Basically, so there are two ways of looking at it. Is one way was like this, I guess. What was this way? We can actually consider uh, each of this as a dice, right? So that was a different case. We are not talking about this dice thing right now. We are just talking about this coins thing. Because this is uh, more related to your naive Bayes theorem, right? Okay, I hope this part is clear, at least how to look at these features, what is the dimensions of this feature. I think that is fine, right? That is clear to us at this part. Okay, so okay, this case is there. I think this thing is there. Class conditional independence, we'll talk about it after some time. But what do you think that okay, let's see this part. So do you think that the same kind of feature will also appear in the spam side, and same class of same thing can be appeared in the non spam side? Is it possible? Yes, right. So if you're writing an email, maybe the same email you're writing it, that might be a spam email, that might be a non-spam email. I think all of us know that whenever, let's say, we are actually sending you some mails, right? So some of the mails will go to the spam folder, right? And some of the mails from the same sender are actually going into non-spam folder. So how does it happen? How does it classify? Because some, based on the probabilities, right, it will say that okay, these words are there into this email, that might go into the spam side, and this these words will go into the non-spam side. So it basically based on the probabilities. So the same mail will have will can be categorized into spam and can be categorized into the non-spam side. So that means how we can decide that it will go to the spam and non-spam, it's based on the probability. So for example, probability of x1 and y1 is 0.01. So can I say that, let's say probability of x1 given the class 0 is 0.01, and probability that x1 given the class, okay, I'll just write it down like this. Let's say y1 equal to 0 and y1 equals to 1 is, let's say, 0.20. So what do you think, like are this probability the complements of each other? Is it necessary to both this probability be the complements of each other?
Not
It
necessary.
is not necessary, right? Yeah, it is not, because these are like two separate things. They might have their own probabilities, and it depends on what is the, okay, where it depends on, because we are thinking that each of this class is a feature, right? So actually this is dependent on this part and this part, right? So x1 and y1. So x1 is one of the coins. Why I'm saying that x1 is a coin or it's a Bernoulli distribution? Because it will have two two sides of it, right? So it's having one zero class and one class, so it can uh, have some probabilities associated with it. Similarly, x1 is a like, it depends on all the bunch of features, like let's say f1 to f10, but each of the feature will have we can consider it as a Bernoulli distribution, so it will have its own probabilities associated with it. And similarly, and whatever the multiplication will be there of the probabilities, based on that the probabilities can change. They not necessarily be the complements of each other. Okay, fine. So that is the thing. Now uh, what is the difference between this case and this case? Okay, let's look at this case. What actually, how this probabilities are assigned to this case? So what do you think is, like, let's say you have three features, right? And you just see that how many combinations are possible of by using these features, and then you have some probabilities associated with that, and the sum of all the probabilities should be equal to 1. Similarly, on the spam side, on the non-spam side also, it is equals to 1. What you do is you just uh, throw dice and you will find out, right, which word occurs and what is the class corresponding to it, and based on that the parameters will be decided, right? uh, that is the case here in this part, when we think about these features are dependent on each other. But if you think that these features are not dependent on each other, that means the class conditional independence assumption is there. In that case, what happens here, the number of parameters which we required to uh, find out, they will become less. So can you tell me what, how many number of parameters we need to find it out in this case? So do you okay, for the class, if it is a two class classification thing, then you have y values associated are 0 and 1, right? It's a Bernoulli distribution, right? So how many, what is the parameter associated, like what estimate, like what is the parameters required to be estimated here? 1, right? Which is the probability of success, or maybe probability which is related to this one. Similarly, for these features, we are assuming that these features are independent of each other. In that case, what we can say is each of this feature will have how many categories? Two categories. So if I wanted to find out, so this is also a Bernoulli distribution. So we can actually say that this will also have one parameter associated with it. So how many parameters are there in totally in this case? Okay, in this case, we'll think of this. Say you have a class, right? So let's say y, when y equals to 1 and y equals to 0. So when y equals to 1, how many features we are having? F1, F2 up to F10. Similarly, how many features it is having here? F1, F2 to F10. So to decide whether, so we need to find out one parameter here, which is the probability of success. Each of this class, we need to find out one parameter, right? So can I say that, let's say P1 hat here, and similarly, how many it will be there? Okay, P1 hat and P2 hat, let's say corresponding to label 1. Similarly, how many? P10 hat corresponding to label 1. Here P1 hat corresponding to label 0, P2 hat corresponding to label 0, and is that. So these many parameters actually uh, we need to estimate. So total how many parameters will be there here?
21.
This 1 plus 10 plus 10, which is 21 parameters. Is that correct? And now if I know that these parameters will be there, I can actually find out the probabilities, and that is the basis for our naive Bayes algorithm, right? So if I know these estimators, and how to find out these estimators, which is the method we generally use it, it's a maximum likelihood estimator, right? uh, Okay, there might be some problems, questions on maximum likelihood estimate. I hope all of you know how to calculate the probabilities or estimate the parameters using the maximum likelihood estimator. Generally, okay, maybe I'll just talk about in a brief maximum likelihood. So in this case, what do you find out? What do you try to find it out? What is the probability of x given theta, right? Or theta given x? Okay. Anyway, what is the likelihood here? I'll just not go into so many details. So how to likelihood is basically it's a product of. Okay, I'll just take some examples better, right? So let's say you have some n samples which are coming from, let's say, IID distribution. In this case, let's say I'm saying that it is a Bernoulli distribution with probability of success p. Uh, this is the distribution for what? A sample or population? It's a population distribution, right? We are saying that these examples x1, x2, xn, these are the samples. These are coming from this population distribution, which is a Bernoulli p, and this is what? This is the probability of success, right? And this parameter we need to estimate. So we need to estimate this parameter based on these samples. What to do in this case? So we know that the samples are coming from this distribution. What is the likelihood in this case? Likelihood will be product of I equals to 1 to n. So n samples will be there into fx of x given theta, right? That is the likelihood. What is this actually? The probability distribution, right? Or PDF. PDF in case of a continuous distribution, or PMF. So for each x1 here, what is the this is a Bernoulli trial, right? So, and it is coming from this, right? So what will be the uh, what we need to find out? Let's say in this n examples we have w1s, then how many zeros will be there? N minus w, right? So can I say that it will, let's say, p1 to the power w into 1 minus p to the power n minus w. This is my likelihood. I hope all of you understand this part. What is it? And what is the, then what do you do then? You just find out the log of the likelihood, and log of likelihood will be if I'll just take log of p to the power w into 1 minus p to the power n minus w. Now, in this case, okay, this is important. Okay, maybe this is important because maybe it will, this kind of questions might come into your exam. So I'm just, that's why I'm just taking it. So what is the log here? Basically, it is log of p to the power w plus log of 1 minus p to the power n minus w, and then this will become w log p plus n minus w log of 1 minus p. This is your log of L. What is the next procedure in this case? We just try to find out, either you can do the negative log likelihood and then you try to minimize that function, or what else is there? You can just take this log likelihood and try to maximize it. And how to maximize it? Differentiate this with respect to
W.
W or P?
W. W is the
No,
variable.
P, right? P is the variable, right? W is like number of
Okay,
ones.
P is the probability. Oh.
Right. Now, W are the number of ones in the data set. So basically, I'm trying to say is like 0, 0, 1, 1, 1. This is a sample coming from Bernoulli P, right? In this case, what is the likelihood? P to the power 3 and 1 minus p to the power 2, right?
2, yeah.
So W is 3 here, and n minus W, which is 5 minus 3, which is 2. Right, so that's what W here is. So here P is the variable. So differentiating with respect to P, what is the differentiation here? W divided by
W
P
by P plus n minus W
by
divided by 1 minus P.
P and minus of 1, right?
Minus of
Because 1 minus P we will
Correct.
have to differentiate later, and that we equated to 0. So can I say that it is W by P equal to n minus W upon 1 minus P? So basically this will become what? 1 minus P times W into P into n minus W. So this will be W
W equal to
PW
NP.
NP minus.
PW.
So basically this PW will anyway get cancel. So what is the P hat here? W
W by
upon
N.
N. What does that mean? This is actually number of ones,
Success.
yeah, successes in sample.
Sample.
Divided by, like, or maybe I can say the fraction of ones, right? Fraction of ones in the samples. Generally, it's a this is true for Bernoulli distribution. So now in this our case, when we said how to find out this probability of success for this class Y, or this is what this actually says what the fraction of maybe ones in a label, right? Is that correct? How many positive classes are there in the labels? So if you have 100 samples and if you have 60 or if you have a data with 100
60
samples,
ones.
yeah, so 60 ones and 0. So that means what is the estimator for this?
0.6.
0.6, which is basically, can I say that summation of how many ones are there, right? So this is the indicator variable and divided by total number of samples, right? So if you just see this, I think we have, okay, it's not here. This is correct, divided by n. So basically fraction of spam emails in the data set, right? So how many ones are there? Okay, yi equals to 1, right? And divided by n. N is what? Number of samples,
Total.
right? Okay. Similarly, for each of the feature, we'll have to calculate this p1 hat. So what is this gives me, like, how can you find it out? Again, it will be a Bernoulli distribution, right? The same it will also have the same kind of structure, right? So how many number of n's are there out of this total n, right? But what is the difference here? Okay, how to find out this fraction? Shall I look into all the data set, or shall I look into only the data set which is containing only y equals to 1?
Y equals to 1.
1, and in that y equals to 1, how many times this f1 appears to be 1, right? Okay, I'll get simple examples. Let's say f1, f2, and y. So if you have 1, 0, 1, 0, 1, fine. I have 1, 1, 1, 0, 0. You have 1, 0, 0, 0, 1. Okay. So what is the, okay, in this, okay, this is a smaller data set. Can you tell me what is the, okay, and let's say this is p hat is corresponding to this estimator parameter. Okay, we'll have to find out separately. What is the p hat here? What is the estimator for p hat here? Can I say that it is 3 by 5?
Yeah, you can say that.
Okay. Then what we are saying that in that coin we have when y equals to 1 and when y equals to 0, in that we have two features, f1, f2. Here we also have two features, f1, f2. Okay, the probability associated with this coin is, let's say, p1 1 of hat. What does that mean? This one is for feature 1 and this one is for the label 1, right? Similarly, we have p1 of, oh, sorry, not p1, p2 of, like this, right? And we have p1 0 hat, p1 sorry, p2 0 hat. We'll have to find out these fractions, right? So what about this? Out of the positive class, right, how many times one will occur, right? So what is the positive class here? Can I say that only this part? In this part, how many times one occurs for the feature 1?
Twice.
So what is this probability? Or
2 by
not
3.
probability, sorry, this is not a probability, this is like parameter, like what is estimator for this parameter. So
2
can
by
I say
3.
that it is 2 by 3? Yes. What about this?
1 by 3.
So in that case, where I'll have to look into, so we are looking only where the labels are 1, only these 3. And what is how many ones are there for this this part? It is this portion. So can I say it is 1 by 3? Similarly, what is p1 hat of 0? So where will I'll have to look at now? I'll have to look into this side where the label is 0. Now I'll have to find what is the fraction of ones for this feature.
1 by 2.
1 by 2, and here it is
1 by 2.
1 by 2. Is that fine? So this is how you have found out the probabilities. So these are the parameter estimated for this. Now if you have given one text point x test, which is, so let us say these were x1, x2, x3, sorry, x4 and x5. If I given you one x test which is let's say, okay, I think we don't have so many features. So let's say you have 1 and okay, 1 and 0. Okay, I need to find out the prediction for this. How to find out? By using the Bayes theorem now.
Label is 0, right? Yeah.
Label is,
Label is 0.
how you found out this part? So okay, I think we will have to understand this. Okay, so we have found out this all this these things, right? Estimators. Okay, these are the estimators here we have found out. Do you agree with this part? What is this? Did we do the same thing there, or so you just understand this notation? What is this notation corresponds to? Pj hat of y is what? J is for
Feature.
feature, and y is for the corresponding labels. So this is the part, right? The first feature and the corresponding label. The first feature and the corresponding label. Is that correct? I hope this is fine. And how do you find out this value? Indicator that, let's say, the value of feature equals to 1 for that example 1, and this label is corresponding label is 1, we'll have to find out that many numbers divided by total number of y1 equals to 1. That is how we found out. Okay, now the prediction part is what? We'll have to find out these probabilities. Given the x test, what is the probability that y test equals to 1? Fine. So we just have to find out, given so y prediction, let's say y predict equals to 1 given x test, and we need to find out the other probability, which is y predict equal to 0 given x test. Fine. And whichever is the probability, let's say if this probability is higher, what we predict for this label?
It's a
1, right?
complementary 1 minus.
No, 1, right? Then no, what I'm saying is, if the value of this comes to be higher than the value of this, the probability value, then I'll automatically predict the label for that test is equal to 1, right? Correct, na?
Okay.
And if this probability is lesser than this, then I'll predict it this label as 0.
1.
0, right? Because the probability that this picture is equal to 0 given the x test is higher than the probability of this picture is predicted equals to 1 given the x test. So if the whichever the probability is higher, we'll predict that feature like that. So if this is the condition, then I'll predict at 0. If this is the condition, then I'll predict it as 1. Right? This is the simple decision rule where, so this is a decision rule, right? This is a decision or prediction. We are doing the prediction based on this decision. Now, but how to find out these probabilities? That is the case. So these probabilities are we can find it out using the Bayes rule. So what is the Bayes rule? Probability of A given B by Bayes rule. What? How will you write it?
Probability of B given A into probability of A
Into probability of A.
probability
Right.
of B
By
probability of B.
yeah, probability of B. Right. So this is actually a total probability, and this is so generally this is like that. Actually, probability of A intersection B and divided by, so we can actually find it out like that, but that's okay. We are not diving into the details. And what is, so can I use this rule to find out this thing? So by using this, okay, this is a Bayes rule, a general Bayes rule. Can you tell me what should I write it here for this part? Probability of,
Y prediction equal to 1 given
can I say now
x test.
x test given y prediction equal to 1, correct? Into probability of y prediction equal to 1. No, huh? Is that correct? We are considering this as A,
That is A, the other one is B.
B.
Okay.
So if I just use the analogy here, can I say that this is the correct thing?
Yeah.
Every time, right?
Yeah, and divided by
And divided by
P of x test.
P of x test. Is that correct now? Okay, fine. Probability of x test. And what about, okay, I'll just write a little bit closer. It's probability of y prediction equal to 1. What about this side? How will I write that part? Probability of x test given y prediction equal to 0 into probability of y prediction
Y
equal to 0
prediction to 0
divided by probability of x test.
x test.
So can you say that if I wanted to compare these two quantities, these two are different quantities, can I say that I just need to compare only the numerator? not the denominator. Why?
Yeah.
Because the denominators are the same on the both side. If I ignore this denominator while comparing, because anyway I need to compare the numbers, right? Here we are getting the probabilities, and we know the probabilities are always between 0 and 1. So this probabilities, actually if I just calculate, some value will be there divided by this value. So anyway, these are some numbers. So if I wanted to compare only these two, possibly these two values, I don't need to care about the denominator. Why? Because the denominator on the both sides are the same. So can I say that only I need to compare these two values? Fine. This case is okay.
Yeah.
Right. No. Okay. Fine. So I need to compare these two things. So this is the case. How to find out these probabilities, and these probabilities will be basically find it out by using this. Uh, uh, so X test is what? All the feature values given y test equal to 1 into probability of y test equals to 1. So y test equal to 1, this we already found out the parameter for this, right? For the y, where we have found out here, p hat. Now what was the p hat in this case? It was 3 by 5. So it has already been there. For this X test, 1 0, and I need to find out for when the prediction is 1, what should I use it? I should use these probabilities, right? Correct? These probabilities, product of these probabilities. So what is the probability that X text given prediction equals to 1? So what does that mean? When I am having y equals to 1, what is the probability associated with this part?
2 by 3.
So first feature is this is f1 and this is f2, right? I need to find out the likelihood or the probabilities. How it will be? 2 by 3 into this feature 1, right? So 2 by 3 into
1 by 3.
1 by 3 or 2 by 3. This is 0, right? This is a probability. 1 by 3 is probability for when it appears to be. Okay, what are these probabilities? Probability that it will appear as 1. What will be the probability when it appears as 0? So it is 1 minus p 1 hat of 1, which is 1 by 3, right? Similarly, here it is 2 by 3. Are you able to appreciate this part? No? Okay, f1 is a feature, right? It is having, it's a coin. Can you consider this as a coin? Right?
Okay.
For that coin, what is this probability? This is the probability that it will be a success, right? That means it will give me the value as, okay, I'll just write it down. So possibly f1 equal to 1, then I'll say that it is p1 hat 1. What does that mean? This one is for feature equal to 1, and this one is for prediction equals to 1. But basically this probability is for when this coin gives me the value 1. But what is the value of when f1 equals to 0? What should be this probability? 1 minus p1 of 1 hat, right? It's a like simple thing. Like we when we say that this is the coin and it is having p hat as the probability of success, what is the what is the sorry what is the probability that y equal to 0 then?
1 minus p hat.
Similar case we are actually applying here. What we are saying that if f1 equals to 1, what is the probability corresponding to this is p1 1 hat. What does that mean? This why this 1 1 are coming is because to show that this is related to the feature 1 and this is related to it belongs to that class 1, right? No. So then in that case, if I wanted to have this f1 of f1 equal to 0, in that case, what is the probability? 1 minus p of this, right? I hope you're able to understand this. So if I have this f, the value of f1 equals to 1, what is the probability? Just 2 by 3, right? But what if I had f1 equal to 0. What was the probability? It was equal to 1 minus 2 by 3, which is 1 by 3, right?
Yes, sir.
So if I have these two features, f1 and f2, and I have the probabilities on the y equal to one side, then what should be the probabilities I should multiply here? So I'll just, okay, 1 minute. Okay, so can you tell me now what are the probabilities here? So probability of x test given prediction of y1 is basically the probability of, let's say, x test equal to what is 1 0 given y prediction equal to 1 into probability of y pred equal to 1. So basically I'll just write it down like this. It is p1 1 hat into 1 minus p1 1 hat, right? This is what this probability is, uh, into y prediction is p hat, number of ones in the y data set. So what is this p1 1 hat? Sorry, I think I have just done it wrongly. P2 1 hat. Fine, right? This is corresponding to feature 1 equal to 1. This is corresponding to feature 2 equal to 0. Right? And what is this P1 1 hat from this? Which is 2 by 3. Correct, na? This is 2 by 3. This is 1 minus 1 by 3, because P2 1 hat is 1 by 3. So we need it to be 0. So it is like that. And now the prediction on the y side is, this is actually p hat, which is p hat is 3 by 5. Okay, it is 3 by 5. So I'll just write down it's 3 by 5. Now similarly, so this for probability of x test equal to this. Similarly, I wanted to find probability of x test equal to 1 0, but given now y prediction equal to 0 into probability of y prediction equal to 0. So this part is 1 minus p hat. What about this now? This will be p1 but 0 hat, right? This is feature 1, this is feature 2 into 1 minus p2 0 hat. Okay, so what is p1 0 hat here? This half. And what is 1 minus p2 0 hat? This is 1 minus 1 by 2. Again it is 1 by 2. So it will be 1 by 2 into 1 by 2, and this is how much? 1 minus 3 by 5, which is 2 by 5. Now I'll compare these numbers. So in comparison, what I'll do, so basically this will become, okay, I'll just write it down all again. This will become 2 by 3 into 2 by 3 into 3 by 5, and this part is 1 by 2 into 1 by 2 into 2 by 5. So this 3 will get cancelled, let's say. This 2 get cancelled. So we are remained with 4 by 15, and here it is 1 by 10. So which is the greater one? I think this is a greater probability, right? 1 by 10 is basically 0.1, and 4 by 15 is like 0.2 something, right? 0.2 and whatever the values will be there. So which one I should predict now for this given feature? So this basically, this value comes out to be 4 by 15, and this value comes out to be 1 by 10. and this is a higher value. So what should I predict now as a label? 1, right? So y prediction equal to 1 because it will have the higher probability. I hope this is fine. Okay, you need a little bit of understanding to this. Like you may just go through it once more time. I guess if it is not clear at this point of time, do some problems, right? That will be better.
Yeah, yesterday's session and today's session, will you be able to upload to YouTube?
It is uploaded on the YouTube anyway, right? Today's session also it's already uploaded.
Yeah, I'm looking at the link in the calendar. It
Oh,
is
it is
not
not there.
there.
Okay, okay, just a minute. I will just
Yeah.
right now. I'll just add it into the calendar. Okay, I did one mistake last session, right? So I'll just tell you what mistake I've done. Maybe those who have attended my session, maybe they in the solve with us session for week 8, while we were discussing the parameters. Oh, sorry, not this one. I'm sorry. Just a minute. I will just wait for 5 minutes. No, miss 5 minutes means like don't go right now because I'm just telling you which mistake I have done because that was important. Maybe it can. Where is that? Okay, the slides which you have uploaded for this solve with us and all, have you gone through those? Because there are certain numericals are available there. You can just go through them also. Just wait for a minute. I just wanted to find out that somewhere I just asked to find out the number of parameters which are required to be found out, right? For any algorithm, I think. Just, okay. So I think I asked you to find out the if you have the Gaussian features instead of the Bernoulli features, what was the number of parameters you need to find out? I think that was the question, and I said you will have to take the covariance matrix as uh, the number of features, something like that. I just right, and I
Yes,
said that you will
all.
have yeah in the solve with us, and I said you will have to take. We'll have to take the whatever the upper diagonal elements are there and plus the diagonal elements, right? That kind of question
Yes,
was there.
yes.
If I yeah, so there the mistake there was the covariance between the variables will be equal to 0, right? So you don't need to find out all. Do you understand that part? So since we are assuming in naive Bayes theorem that it is a class conditional independence. If you are okay, I have now my
Yeah, got it.
right. So I did a mistake there while I think you guys were doing another mistake, that you will be finding out the more than like all the parameters, right? And then I said you should be doing only the left side of the parameters. Something I just told you here, not here also, I guess. This was easier, right? So you can find out how many parameters we need to find out here in this question. So how many labels are there? Okay, how many classes are there here? 3 classes, 0 and 2.
Yes, sir. Two for classes.
Yeah, 2. So we need 2 parameters for the classes, and you have the binary features f1, f2, f3. So how many parameters you need to find it out? This is important question because this might come to your quizzes, so you just try to think about it, right? So okay, how does it will look like? So you have 3 classes, right? Suppose say y equal to 1, y equals to 2, and y equal to 3. So for 3 classes, how many parameters you need to find out? 2, because then the probability of y1 hat, sorry, okay, y equal to 1, let's say 1, probability of y equals to 2 hat, and probability of y equal to 3 hat, that should be, the sum should be equal to 1, right? So that means if you find out only this 2, you definitely will be able to find out the third one. So as we seen in the 2 class classification, if you have 0 and 1 classes, you just need to find out only one. So each of this feature, okay, each of this class, how many features are there? 3. So 3 classes, that means you need f1, f2, f3. So can I say that it's like you have 3 features f1, f2, and f3. So how many parameters you need here? 3 here, again 3 here, and again 3 here, right? So 3, 3, 3. So 9, 9 plus 2 equals to 11. You can write them as, let's say, p1 1 hat, p2 1 hat, p2, sorry, p3 1 hat. Here it is p1 2 hat, p2 2 hat, p3 2 hat, and p, here it is p1 3 hat, p2 3 hat, p3 3 hat. And what will be, so if this is a coin, then you will have p1 1 hat here, 1 minus p1, p2 1 hat here, 1 minus p2 2 hat here. So you don't need to find out these values, right? Because if you know these parameters, you will definitely able to find out this, because it's 1 minus the probabilities. The total number of features should be here, will be 2 plus 9 11. But I think there was a question on this one, right? Naive Bayes. A Gaussian naive Bayes model is trained for a multi-class classification problem that has 10 features and 3 classes. Find the total number of parameters that has to be estimated for this model. So for 3 classes, how many parameters?
Two.
2. And for 10 features,
Two.
since they are the Gaussian naive Bayes, so each feature, if it is a Gaussian feature, each of the feature will have what? So each feature will have 2 values, right? One is mu and sigma square.
Variance. Yeah.
Yeah, right. So, but we generally find out like this mu and the sigma, right? That pair in this classes. But since we are actually saying that these are the class independent, so each of the feature is not dependent on another feature. So when this matrix, if you see, what this matrix will be, sigma 1 1 square, this will be a vector. Okay, this is a vector of mu's. If you have 10 features, how does this vector will look like? It is mu 1 mu 2 up to mu 10, right? This is a vector. What about the sigma? That is sigma 1 1 square, sigma 1 2 square, up to sigma 1 10 square. And similarly we have sigma 10 10 1 is actually sigma 1 2 square, and it should be sigma 10 10 square. That we, I think we have discussed this part, and I said that you should be doing this and plus all these features here, because since it is a symmetric matrix, because covariance matrix is always a symmetric matrix, you don't need to find out this. But again, you don't need to find out these parts also, because since it is, these features are independent of each other, independence is always giving me what? The covariance equal to 0, right?
Zero. Yeah.
And that's why this sigma will actually will be only a diagonal. So sigma 1 1 square, sigma 1 2 square, and sigma 1 10 square, right? No, it's not 1 10, 10 10 square, sigma 2 2 square. So variances across each of the variable, right? And this part will be 0 and this part will be 0. So how many features now you can see, you need to, or how many parameters you need to estimate now? 10 parameters for mu, right? Mean. And how many parameters for sigma? 10 only.
Yeah, then
So total will be 10 plus 10 20, and plus
2
2 for the
classes.
so can we say that the final answer should be 22? 22, or what else is there? Okay, I think we will go through this once more. Right? This was the case, right? In the Gaussian thing. If you have two classes, y1, y0, you will have one mu1 and you will have one mu0, and you have corresponding covariance matrix, right? I hope this is fine. So you need 10 here, you need 10 here, plus you need this 2 and plus this 2. So I think the number of parameters will be, uh, in this case, how many will be there? Let's say you have 10 features. How many features are there here? X1 to xn, xy is d, and y0. Yeah, it will, you tell me now in this case.
22, sir.
10 here, 10 this side, but variance is the same, na? Variance is same on both the sides, right? If you are saying that, assuming that the sigma is same for the both the things, then how many will be there now? Features 10
three.
plus 2
Yeah.
plus 1, right? I hope it is fine. Okay, you just think about this, like estimators here. P hat is for the class, mu1 hat is for sample mean of data points which are labeled 1, mu0 hat is sample mean of data points labeled 1, and sigma will be that covariance matrix. But again, it will have only uh, how many features, or how many, what will be this diagonal entries? Only diagonal entries we'll have to calculate, right? This covariance matrix will be a diagonal matrix. So accordingly, you'll have to find it out how many diagonal entries will be there. Okay, I think that is one part. Another part is that maybe I'll share you these slides also, which are there. Can understand. Okay, this, but I think I'll this don't use these slides, maybe because you might get confused at some point of time, right? So anyway, I'll share the slides with you. Maybe you can use it for interim exam preparation. For now, don't use these slides. Okay, you just use the slides which are there in the in the lectures, because most probably the questions will be coming only from the notes which are there in the lectures. I've shared these slides for additional practice. If you have time and if you think that you're not going to get confused with that, then you can refer to those. Okay. Any other questions from your side? No questions? Okay. I think I still have not covered everything, but I just tried to give you the exact like what are the algorithms, you can solve the questions based on these algorithms, probably the numerical ones. Still, you'll have to do a lot of you'll have to go through all the slides which are there in the lectures. You just try to understand what are it is said there. Yeah, important topics are okay. I think everything is important anyway because I'll have to check whether is my screen visible.
No, sir.
No, right? Okay. You're sure, right? It is not visible.
Not visible.
Okay. Because if I see the question paper and if I'll tell you, then you might see the question paper if it is.
Really not visible, sir.
Okay. Yeah, just a minute. I will try to see. Maybe I'll tell you what are the topics you might need to focus on. You can just try based on the question paper which is there. You can focus on those topics only. Okay, I'll send out the mail. Okay, mail or I'll post it that answer on the discourse, right? Exact solution for that.
Yeah, sure.
Yeah. I don't know. This internet is slow. Okay, so you'll have to focus on the linear regression part, like how to find out its solution. Maybe you'll have to practice to how to do these calculations, right? Uh, Simple calculations will be there, but still you'll have to find it out. The solution might be provided to you. You'll just have to uh, solve that, like solution in the sense uh, that maybe the gradient and all will be there. Again, you'll have to know how to solve this kernel regression problem. So kernel regression also solving in the sense you should be focusing on how to solve numerically. Numerically, given the kernels, given the coefficients, right? What is the solution for kernel regression? Is summation of alpha I into ki, right? Kx into x prime or x test, right? That is the solution. So how to get the answer, that you will have to uh, do it. Then ridge regression, you will have to understand the concepts. The numericals will not be there on the ridge regression side. K nearest neighbor, you will have to know how to predict using the K nearest neighbor. I think I have covered that cross validation techniques. Cross validation techniques also, you know, right? There are two cross validation techniques. One is K fold and another one is leave one out. What is leave one out do?
It will leave one
One and we'll see the prediction based
denominator.
on the remaining ones, right?
Yeah.
You'll have to understand that, and you should be able to apply it on the maybe k nearest neighbor or the distant trees, whatever there is there. So that kind of question will be there, and you will have to able to find out the entropies, entropy and information gain. Fine. The values will be provided to you, but entropy formula you should be remember. Right? You should remember the entropy formula. What does that p there? What does that 1 minus p there in that formula, right? What is the formula? Minus of p log p. Uh, so minus, if I take it common outside, it is p log p plus 1 minus p log of 1 minus p. So that formula you should be remember, and you should be able to find out the information gain based on that. Then you will have to find out the number of features as we discussed today, right? We should be able to find out the number of features, not number of features, number of parameters. I think these are the topics. So mostly these are the topics which are important. You should be able to numerically solve the linear regression problem, numerically solve the kernel regression problem, how to find out the number of parameters in a naive Bayes classifier thing. uh, what else I said? Ridge regression, you should be able to understand it conceptually, like where is the ridge regression solution lies, right? I think, I hope you know what is the ML estimator for the regression. And so do so which is the best solution between the ML regression, so W hat ML gives, right, only like normal regression, and what is the regression gives? So which is the best solution among these two?
Rich.
Ridge is better, or the normal is better? Better in the sense which will have the uh, so corresponding to the squared error, right? Mean square error, which is the better one? So, or which is having the minimum square error loss? Ridge one or the normal one?
Bridge one.
No, the normal regression will have the actually the minimum loss, right? Ridge regression actually, when it's an optimization problem where you have the constraint optimization, right? So you are saying that with the loss of squared error, but can I get the better solution, right? Better solution in the sense we are actually constraint, we have some constraint over that, right? When you say that your regularization parameter, what does it do? It will try to some features, it becomes like redundant now, right? So, or maybe they're not useful, so we just reduce those features, but the squared error loss is actually better for the normal regression, right? And
Yeah.
what about the lasso? Will remove the features because the coefficients corresponding to those labels. So suppose you have w1 x1. What is general equation for y? The best fit line is, let's say, w1 x1 plus w2 x2 plus w3 x3, right? That is your uh, general, let's say, function. In lasso, what you do, maybe you will give that w3 as 0. So what does that mean? That x3 we are actually removing. We are only focusing on the 2. But with that loss, right, with that loss of attribute or the feature, what we are actually trying to do here is, the mean squared error loss is actually increasing, but uh, what we are gaining from it, what we are gaining, dimensional reduction basically, right? We are actually getting the lesser dimensions to calculate. So maybe I'll just show you the diagram. That is the important one to understand. So this was the understanding, right? W hat ml was my, so you have this w1 w2, we had this solution w hat ml. This is basically the solution which gives the minimum value, right? We are adding one extra parameter here, and we'll try to solve this now with this constraint. So this is a constraint optimization problem. I hope all of you have completed mlf, and we had that. Have you completed mlf? Week 8 was the week which was based on the uh, unconstrained optimization, right? And those who are in the
Yes.
MLF also, I think they know week 8 is the unconstrained optimization problem. And in the unconstrained optimization, we just have to solve only this part, right? The objective function. In the constraint one, what we are doing is we are saying that I'm not going too far for this WML space. We are restricting this W space. So we are restricting it here. The actual solution is here. The actual solution gives me the lower squared error loss, right? But we are saying that I just wanted this W's into this space only. And now what we are doing is uh, so we are actually what we are doing is we are trying to go near here and like near to this part because we wanted this solution to be here, and in that case this regression solution actually is not a solution which gives the lower minimum squared error loss. Fine, but what we are actually achieving here is maybe the features which are not more important to us, we are reducing them, right? And same with the lasso, what we do is we are removing the features, like because we are the coefficients corresponding to those features are becoming zero. Fine, so lasso also will not give the lowest minimum mean squared error loss. Fine, this is the important topic because the question might come from that. You just understand it, maybe you go through this lecture once more. I hope this is fine. Otherwise, you know how to solve this regression problem, right? Given the data and given the labels. What is the solution for this? Solution for a regression problem? You know? No. Okay, so if you have not done that, right, you just try to solve some problems. I think those will help you in this case. Because in the lectures, the numerical problems are not solved. So what is this part? This is solution, right? Xx transpose xy. This is a solution for, I think this is week 6. I'll go to week 5. So this was the problem we had, and this is del f of w. How do you find it out? It's a gradient, right? If I know the gradient, what will be the solution now? W star will be xx transpose xy. So what is this xx transpose pseudo inverse? Actually, you can think of this as inverse into xy. So given, if you have given the data set which looks like x and y, can you be able to find out this w star? So you'll have to solve it numerically. How do you solve it numerically? First of all, you will take a x vector, you take its transpose, uh, find its dot product, then find its inverse. So you should be able to find out the inverse. Let's say for simple matrix, maybe two cross two matrix, but you should be able to find it out. I hope you all of you know how to find out the inverses of the matrices, and then you will have to calculate this solution. So that kind of problem you can expect in the tomorrow's exam, right? So how to find out solution, how to find out this, maybe the gradient descent. So for that, you should understand what that x feature is, what is the length of the feature, how to find it out, its transpose, what is, how does this w vector looks like. So this is the general x transpose will be x1 x2 xn, this will be w, and this will be y1. So basically y1 equal to x1 transpose w1. What does that mean? So it will look like w1 x1 plus w2 x2 plus w3 x3 equals to y1. So this calculation you should be able to do it. That is one of the problems in tomorrow's exams. So you should be solving it, those kind of questions there. Right? What else is there? I think kernel regression. I said
For
about the
lasso, there is no closed form solution, right, sir?
yeah, there is no closed form solution.
Uh,
But you know, right? The mean squared error will be
yeah, yeah.
lesser. It will be like higher, right? So how to choose? Uh, how to choose the uh, solution, right? That is based on the constraint. So you'll have to look into the constraints. So lasso will not have the closed form solution, but generally you know that like you will get a sparse solution where you know that coefficients are becoming zero. whichever the coefficient becomes 0, that means the feature in anyway it will become 0, right? Because what you are trying to do there is in supervised learning, you're trying to fit a linear or line, right, into the data set. So what is the equation of line generally? Y equal to w1 x1 plus w2 x2 plus w3 x3, like that, right? If you have d features, then it will be w1 x1 plus w2 x2 up to wd x3. So basically how it would look like, I'll show you this part. And what does lasso do? I'll tell you that also. So your y prediction should be equal to like this: w1 x1 plus w2 x2 up to wd xt. Fine, right? And what is, we know how this data set will be. So you have x here, you have y here, right? Corresponding x and y. So where the x1, x2 are the features, or the what do you think? They are the features, or they are the uh, data points?
Data points.
They are the data points, right? So let's say each of these data point will have two features. Okay. So how this x1 will look like? Can I say like let's say uh, f1 f2, x2 will be some f1 f2. So if I wanted to create a matrix, how this matrix will look like? X will become okay. What is the dimension of this matrix? Can you tell me?
2 cross n. So,
D cross 2, right?
uh,
Oh, sorry. Okay, sorry. Uh, n cross 2, right? If I wanted the matrix in this format, but basically, how do you do that? So it is generally it is a D cross n matrix. We are looking at it, right? So it will become this way. So two features, and let's say okay, I should say n examples, right? Examples. And how is your w vector? What is the dimension of w vector? Hmm? So basically it is n, right? N values you should have, right? No,
yes, sir.
is this x1? This vector is x1, is x2, and how many vectors we are having? N vectors. Then you should have this w as, can I say that it is w1, w2 up to wn. Fine. So this can be n cross 1 vector. I hope this is fine. And if I have this xw, that should be equal to, so that is this line, right? Y hat. And then you find out the error. So generally our error will be y hat minus y, or y minus y hat, whatever you want to do, because we are taking the squared error. And over all the examples you do, and then you find out the minimum error. But that is your general look, like this data will look like. And what is the y vector looks like? It will also be n cross 1 vector, right? For each of the example you have one prediction. So your solution, which is here, so you can just think about this part what I showed here. So it's like this. So x transpose will be x1 x2 xn, and this is w, this is d cross 1, and here it is n cross 1. Because okay, I think I have done some mistake here. It shouldn't be okay, sorry, this will be not like this. So if you have two features, then how many w's are there? Basically it is w1 f1 plus w2 f2, right? Correct na? Then this is y1 hat. right? So your w vector should be like, sorry, this is wrong, should be w1 w2 cross 1, and then your corresponding y will be n cross 1, like how many number of examples will be there. Now this is what we have to understand. So if you are given some feature x and corresponding y, let's say 1 2 3 4, and let's say 2 3 4 5, in this case, if, and what is the solution now? Let's say this is the solution, right? X transpose xy. So w star, you wanted to find it out. W star is x transpose inverse xy. In this case, can you tell me what is uh, x? How does this x will look like? And okay, what is the dimension of w here? No. This is important to understand, right? How to do this. By looking at this, can you just tell me now?
It will be
Why?
similar, sir.
Why is what kind of,
Distance.
is this like, okay, in this example, y is, can I say it's 4 cross 1? Y is 4 cross 1? See, it's very like, okay, y hat will be basically what, like it will be wx1. Let's say I'll not use x here, let's say if I use, right, and these are the examples, x1 x2 x3 x4. If I use, so can I say that y hat will be wx1? Or if I just use x here like this, can I say it, what is the what should be my prediction? It should be like w times 1, here it is w times 2, here it is w times 3, here it is w times 4. And what is the error here? Y minus y hat will be 2 minus w, 3 minus 2w, 4 minus 3w, and 5 minus 4w. Is that correct? That should be my deviation, right? And if I take the squares of it, that will be the error. And now I'll take a sum of all these errors and then find out what is the minimum w. That is actually problem we solve it. So in this case, if I have 4 cross 1, what is the dimension here for w? It should be 1, right? Because you need only one w here. If you just think about it, my equation will be like this: w, let's say w star x. That w star will be the minimum thing. So w star x, since you have only x, one x. If you had two x's, let's say x1 x2, if you had 0 2 4 5, then this will be w1 x1 plus w2 x2, and in that case that vector w star will become what? W1 w2. I hope this is fine. Okay, let us see. We'll stick to this part now. What is the solution here? Okay, this x will be what? X will look like. Will that look like 1 2 3 4 like this, or will it look like the the vector like this? This is the vector, right? 1 2 3 4. Anyway, see, in this case it's a single dimension, right? So if you take x6 transpose like this, or if you have different thing, that is also fine. But how to decide whether it is correct or not? You can actually decide based on this also. You have this 4 cross 1 vector, so definitely if I wanted to do the multiplication, if this become a 1 cross 4, right, that means one column into the 4, then only we'll be able to reach out to the sum solution. Because for any vector multiplication or matrix multiplication, you need these two things same. So your x in this case will be this one, 1 2 3 4. So x will be 1, 2, 3, 4. This x transpose will be 1, 2, 3, 4, and then you will have to take a inverse of this, and this x will be okay. This will be equal to, what is it? 1 comma 4. Sorry. 1 comma 4 will be. I'm doing it. That's okay. Here it's not a problem. Inside this is not a problem. Outside you'll have to understand it properly, because inside anyway it's a dot product between x and x transpose. It anyway gives me the same thing. So it is 1, 2, 3, 4. Here it is 1, 2, 3, 4, and here it's 1, 2, 3, 4 into y is 2, 3, 4, 5. 3, 4, 5. Okay. Now what is this part? 1, 2, 3, 4, 1, 2, 3, 4. I think it gives me 1 plus 4 plus 9 plus 16. So 25 plus 5, 30. So 30 inverse, that means it's a scalar value now I am getting. 30 inverse basically is 1 by 30. So 1 by 30 into this part, whatever. So it is 2 plus 6 plus 12 plus 20. 18, 20, 40. So 40 by 30 will be the answer for W star. I hope it is understandable. Suppose you had two vectors, then or two features. Let's say it is x2 and it is x1 0, 2, 0, 4. In that case, this will become 0, 2, 0, 4, and this will become 1, 2, 3, 4. Okay, I'm just okay. Let's say this is x1, 2, 3, 4, 0, 2, 0, 4, and similarly this will become 0, 2, 0, 4. Now this will be what? This will be a 2 cross 2 matrix. Then you will have to find out the inverse for this 2 cross 2 matrix. This is 2 cross 4 matrix, is 4 cross 1 vector. So you will get a 2 cross 1 vector. So you will get a vector here. So now when you find out the solution, this will be a 2 cross 2 matrix. This part gives me a vector which is a 2 cross 1 vector, and inverse also is anyway this is 2 cross 2 matrix, and then you will just multiply this part, and what is the final thing you will get for W star? So you will get 2 cross 1 vector, right? So you will need to find out these kind of solutions, right? You just practice on this part. This is important to solve as far as tomorrow's quiz is concerned. Apart from that, I think like most of the things are based on your understanding of the concepts. This is the only thing you need to uh, work on it. Fine. Okay, so we'll stop here. I'll stop the recording and stop the streaming. Yeah. So this is what actually I whatever I discussed, right? It's like